Hey everyone, welcome back to 4.4. This is the last section in Unit 3, which is where we're going to build quadratic models from verbal descriptions and from data. So if you'll remember, we looked at max and min back in the last unit, right? They were known as extrema. When we fit quadratic functions to data that we have to model a problem, and we determine the max and the min, that's called optimization. Okay, that's what that process is called. So we're going to look at that in terms of revenue again in dollars, which remember is just the amount of money that is received from the sale of an item, and it's equal to the unit selling price in dollars of the items times the number of items or units actually sold. So the formula we use is R equals X times P. Okay, so R is revenue, X is the number of units sold, and P is the price. We also looked at the law of demand, so supply and demand. Demand states that P and X are inversely related, so as one increases, the other decreases. We saw that with inverse variation. And the equation that relates P and X is called the demand equation. When the demand equation is linear, the revenue model actually turns out to be a quadratic function, as you'll see here. So here's an example. You can pause the video at any moment, read the problem yourself, and unpause when you're ready. We'll go over it together. The marketing department at Texas Instruments has found that when certain calculators are sold at a price of P dollars per unit, the number X of calculators is given by the demand equation. X equals 21,000 minus 150p. Find a model that expresses the revenue R as a function of the price P. So we know our equation is R equals X times P. R equals number of units times price sold, okay? When they say express the revenue as a function of the price P, that means X is going to go away and all we'll be left with is P. How is that going to happen? Well, X is equal to 21,000 minus 150p. So all I'm going to do is replace this X with that expression, 21,000 minus 150p. So I'm going to have R of P, right? Normally we have like F of X or R of X, and that's because the variable in the expression is X. Well, here, the variable in the expression is going to be P, because we know R equals X, and X is 21,000 minus 150p times P. So that expression represents the revenue as a function of the price P. And of course, we can distribute the P here. So P times 21,000 is just 21,000p, and P times negative 150p is negative 150p squared. So that's our actual equation, okay? Now, what's the domain? So remember, domain refers to the X values. So if you think about it, right, this is saying the revenue is non-negative, so that just means it's got to be greater than or equal to 0, okay? Well, what is X? X is 21,000 minus 150p. It's saying it has to be greater than or equal to 0. So you can sell 0 units, but what's the maximum number of units at that price? So if I solve for P, I would subtract 21,000, divide by negative 150, and remember, you're dividing both sides by a negative, so the sign will switch around. Be very careful with that. Negative 21,000 divided by negative 150 is 140. So that's your domain, which basically says in set notation, P such that P has to be in between 0 and 140. Okay, so the smallest number of units sold would be no units, 0, all the way up to 140. And in interval notation, you would write it like this. Okay, so that's your domain. That means we're looking at 0 to 140 for the price. Okay, and that's dollars per unit. So you can sell, a unit of calculators for no money at all. Maybe you're giving it away, where you don't sell any, all the way up to $140 per unit. Letter C says, what unit price should be used to maximize the revenue? So remember, unit price refers to X, right? Maximize always refers to the Y value. So we're trying to figure out, like, okay, at what price should I use to get the most revenue? So I'm dealing with the vertex here, and I need to find the X value of the vertex, right? Because if you were to graph this equation, it would be an upside down parabola. You can take a look if you were to type in, it was 21,000. We can't use P, so we'll use X, right? Minus 150 X squared, okay? You can't really see that on here, but if I change this to go from 0 to 140, and I don't know, make this from 0 to, let's say, 1,000, actually more than that. Okay, you can start to see it, but it takes a lot. As you can see, it's upside down, right? We're looking for the vertex, which is right there. So we would need to sell each unit for $70, right, to maximize the revenue. But how do we work that out algebraically? So what we're going to do is just find the X value of the vertex, which, remember, the formula is negative b over 2a. So I need to look at my equation, which was this. And I need to find my a, b, and c. So a is always attached to the squared term, so a is negative 150. B would be attached to the linear term, so that's 21,000. And there is no c, it's 0. Okay, so here we've got negative 21,000 over 2 times a. So this is really negative 21,000 divided by negative 300, which comes out to 70. So $70 per unit will maximize the revenue. Okay, so we'll get the most revenue out of that. We know from looking at the graph already, the revenue would be $735,000. So how do we do that now? We're going to take our X, and how do we calculate the Y value of the vertex? We're going to plug in our 70 in for P. So I'm finding R of 70. Okay, and I missed a P here. This should be 21,000 times 70, and then minus 150 times 70 squared. And when you type that in, you end up getting $735,000. So that's the maximum revenue. Okay. In the next example, again, feel free to pause and read, and then you can pick up when you're ready. It says a farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? So I want to maximize the area, right? So picture you've got your rectangle, and I don't know if this is going to let me draw one. Yep, there we go. So each of the sides, the lengths are X, and we'll call the width W, okay? They gave us 2,000 yards of fence to enclose a figure. Enclosing anything is talking about perimeter, or the distance around a figure. We know that for rectangles, you can use the equation 2 times the length plus 2 times the width. Okay? Instead of using L for length, you can use X. It doesn't matter. So I'm just going to substitute in here. I know my perimeter is 2,000, and I know my length is X, and my width is W. Okay, so I want to solve this now for one of those variables. Let's solve this for W. So to solve for W, I'm going to subtract 2X So I have 2000 minus 2x equals 2w. Okay, why am I doing this? So let me talk about that. We need to find the dimensions of the rectangle that enclose the most area. So the formula for area of a rectangle is length times width. So if I can solve this for w, I can just replace that w with my expression, and it'll allow me to figure out the area and the dimensions, which is just asking for length and width. Okay, so I'm still not quite finished solving for w here. I would have to divide everything by 2, and you would get the width equals 2,000 divided by 2 is 1,000, and 2 divided by 2 is 1. So you have 1,000 minus x equals w. All I'm going to do is replace that right there. And we know that L is really just x, right? So you've got area equals x times w. What's w? It's 1,000 minus x. So it's like the revenue problem where we replaced everything and we had all p's there. So what you have here is really a of x equals 1,000x minus x squared if you distribute the x. Okay, so I'm going to do the same thing. We're talking about most area or maximizing the area. So I want to find the x value of the vertex, which is negative b. So b here's 1,000 over 2 times a. So you end up with 500. So now I'm going to find a of 500. And when you work this out, you end up with 250,000. Okay, that would be the area, so yards squared, if each of the dimensions was 500 by 500. So actually, you would have a square, right? The square root of 250,000 is, what would that be? That would be 500, right? So the dimensions are 500 by 500 if you take the square root of each. So 500 yards by 500 yards. Okay, I'm going to skip over the try this. Both of those are very similar to what we just did, so you can try that. We're going to finish off the notes here with looking at some nonlinear relationships. So as you can see here, these are not linear. In 4.2, you looked at linearly related data. So an x and a y, when you graphed it, the scatter plot came out to be kind of looking like a straight line. You can also have nonlinear relationships, okay? So here in the graph on the left, A is positive. As you can see, it's kind of looks like a U going up, right? So concave up. And then here A is negative, and you can kind of see it's concave down and has a maximum, right? So let's look at an example. And you would need to type this into your graphing calculators, okay? So in order to do this, you will need your TI 84 plus, and you'll need to go into the following menus. So I'm going to write down for you where to go. You would, for this first part here, it says a study compared the speed x in miles per hour and the average fuel efficiency y in miles per gallon of cars. The results are shown in the table. So this just means where you see like the 15 and the 22.3, that meant a car that drove at a speed of 15 miles per hour had an average fuel efficiency of 22.3 miles per gallon. So they were able to drive 22.3 miles and use up 1 gallon of gas, okay, and so on. So if you were to graph this, what exactly would it look like, okay? So in order to graph this, you're going to go on your calculator, you're going to find the stat button and then go to edit and hit enter. You're going to type in all those numbers. So you're going to type in all the x values into L1 and all the y values in L2. To look at the graph, you're going to hit second y equals, and you're going to turn your plot on. Okay? Then you're going to choose the scatter plot. So it's the first graph that's there. Okay, you'll see like about 6 graphs. It's the one on the top left. To graph it, you're going to hit the zoom button. If I remember correctly, the zoom button's in the middle, the gray button's at the top. Hit zoom 9, zoom stat. And you'll end up getting a graph that looks something like this. Okay, which as you can see is not linear by any means. Okay, so down here you've got your speed in miles per hour, so you'd want to label that. And then the Y, you would have average fuel efficiency in miles per gallon. And if you would like to, you can go into the window and play around with the window so that you can actually see everything clearly. We only want the first quadrant because all positives. If you make the x min 10 and the x max 70, you can leave x scale 1. That just means count by ones. I mean, you can make it whatever you want. And then the y min is, let's do 20, right? That looks like it's the lowest y value. The y max I made 30, since the highest one looks like it's like 30 point. Oh, actually, y max you can make a little bit bigger. You could probably do about 32, maybe. And again, the y scale you can leave as 1. Okay, that can help you see the graph a little bit better. So now if I want to create a model, that means I actually want the regression line. I want an equation that models that relationship, that's somehow going to tell me like, okay, this curve here, if I was to draw a curve through it, I want to use it to estimate and predict things. So to do that, you're going to go back to the stat button, but this time you're going to go to calc. And you're going to calc number 5. Okay, it's quadratic regression. And when you do that, you just have to hit enter and then hit enter a couple more times, and it will give you a printout. It'll tell you like y equals ax squared plus bx plus c. It will tell you what values to plug in for a, b, and c. So if you do it correctly, you should end up with something like this. And I rounded. Okay, but that is my regression equation. And we're going to use that function to determine the optimal speed. So there's that optimization, right? We want to maximize fuel efficiency. So how fast do we want to go to be able to get the most fuel, right, for our money? So we're going to take our function and we're going to find, again, speed is x. So I'm looking for x, and it would be the x value of the vertex. That would maximize the fuel efficiency. Okay, so I'm finding what speed is this that's going to maximize it. So I'm going to do negative b. B is 0.727 over 2 times a, and a is negative 0.008. And when you do that, you get something like 45.4375. So the optimal speed to maximize fuel efficiency is about 45, 46 miles per hour. So that means if you're traveling at 45 miles per hour, you'll get you'll burn the most optimal amount of fuel without wasting any or having excess. And also be able to go as fast as you possibly can without burning too much fuel. Okay, and that is the end of 4.4. That does it for Unit 3. Make sure you've done the homework, and then there's a test around the corner as well again. And also, please don't forget your projects. Okay. Okay, hope you all enjoy the rest of your day. Please reach out if you have any questions.